I'm going to go ahead and get us started. Hello, everyone. My name is Lisa Stewart. I'm the Chief Administrative Officer here at the Kavli Institute for Theoretical Physics. And it is my honor today to welcome you for a talk by Mr. Carl Fields, who is presenting this year's very first talk for the National Society of Black Physicists Innovate Seminar Series. Today, Mr. Fields' talk will be approximately 30 minutes, and it's presented in webinar format. This means primarily that we will hold questions until the end. And so if you have any questions that pop up for you throughout the talk, please go ahead and enter those into the Q&A at the bottom of your screen, and we will have a moderated question and answer period at the end as time permits. But the next most important thing I have to do is introduce you to Farah Simpson, the leader of the NSBP Student Council, which is also the group responsible for creating and leading this Innovate Seminar Series. So thank you again for joining us today. We hope you enjoy Mr. Fields' talk.
Hello, everyone. I'm Farah Simpson. I'm a part of the Student Council of the National Society of Black Physicists and also serving as the student representative to the board. I'd like to welcome you all back to the Innovate Seminar Series for our very first talk of the year. We're very grateful to have Carl Fields here with us today, and the Student Council is very excited to hear his talk. Thank you so much for continuing to support our series, and we are grateful to have this space for our members to share their research, and we will continue to hold this space for that purpose. I'd like to present to you the President of the National Society of Black Physicists, Dr. Stefan Alexander.
Thank you, soon to be Dr. Simpson. Can I be heard? Am I? Okay, great. All right, it works. Hi, everybody. My name is Stefan Alexander. Yes, I'm the president of NSBP, and it gives me no greater pleasure, to introduce, amongst our very talented cadre of postdocs at NSBP and the NSBP universe and beyond, since he studies the universe, Dr. Carl E. Fields. Well, soon to be Dr. Carl E. Fields, who's a Ph.D. candidate in the Department of Physics and Astronomy at Michigan State University, who's working with Professor Sean Couch. Carl's research focuses on astrophysical sources of gravitational waves, stellar nucleosynthesis, and multidimensional simulations of core collapse supernova explosions and their massive star progenitors. My apologies. Carl is jointly supported by the NSF and Los Alamos National Laboratory and received his undergraduate degrees in physics and earth and space exploration, where he worked with Professor Frank Timnis. In 2020, Charles was awarded the Price Prize by Ohio State University and named to the Forbes 2021 class of 30 under 30 for science. Amongst other things, Carl is also very much involved in music, and we at NSBP look forward to engaging with him. As you know, we are all very multidimensional as an organization. And without further ado, Carl.
Thank you very much for the introduction. Cool. So thank you very much for this invitation to talk about my research today. I'm really excited. I'm going to change the side thing so I can see. Okay. Yeah, I'm excited to be in this space and to share some of the work that I've been doing, to talk a little bit about sort of the context of my work and place it into sort of the importance of other different areas of astronomy, and also just kind of give a brief snapshot of some of the projects that I'm working on. So I'm excited and I'm very thankful to be invited to talk today. Oops. Okay, yeah, so I want to start off with an overview where I kind of bring into light some of the things that I'll be talking about for the work and sort of set up a roadmap for that. So I'll start off with an introduction. I'll talk about core collapse supernovae in general. I don't want to sort of go into the talk without explaining them, to sort of bringing us all to the same page. I'll talk about the explosion mechanism itself, And I'll talk about this problem in the field that we're facing in terms of obtaining robust explosions and simulations and some possible solutions for that. I'll then segue into what I call next generation simulations in grant proposals, where I kind of talk about some of the previous work that we look at in terms of a 15 solar mass star, 3D simulations of that, as well as some ongoing projects that we're looking at different initial conditions for these simulations, as well as actually exploding these simulations, and looking at the different multi-messenger signals that they might produce. So core collapse in general. Core collapse supernovae are about 3 per century for a Milky Way type galaxy. We expect them to be more numerous than thermonuclear explosions, so they happen more numerous than, for instance, the explosion of a white dwarf, so the remnants of a low mass star. And so on the right here, I have a diagram showing a simplified diagram showing some of the different stellar evolutionary pathways, where we're going to be focusing on massive stars at the top, which are expected to be the end fates of stars that are about 8 times the mass of the sun, so 8 solar masses or more. So these are the stars that we expect to evolve and become red supergiants, so a late evolutionary phase of their life, and then explode as type 2 supernovae through core collapse. And so I'll mention what core collapse is in more specific, but this is kind of the idea, the type of stars that we want to focus on. They produce a ton of neutrinos. They have very large kinetic energies on the order of about 10 to the 51 erg. I still don't know what an erg is, but I know we use it to measure energy. And it's 10 to the 51 erg is about 1 beta. So that's kind of an energy unit that we use for these explosions. So I want to argue that core collapse supernovae are important to many different areas of astronomy. And so one of the ways that they're important is through galactic chemical evolution. So they can produce different elements. They can play this role of sort of stellar feedback in different situations. And they're also important in producing compact objects. So at the end of this explosion, you may have a remnant that's left over that might be a neutron star or a stellar mass black hole in some cases that can actually have huge implications for the evolution of galaxies overall as well. And so those remnants themselves can actually produce multi-messenger signals. And so multi-messenger, meaning so electromagnetic as well as gravitational wave radiation. And so you can see something like neutrino emission from these explosions, and you can measure them potentially with current and next generation gravitational wave detectors. And so they're very important in different aspects in different areas of astronomy. And so sort of motivating some of the reasons why we look at them. So the explosion mechanism itself, right? So how do they explode? So this is probably the most complex slide that I have, but I wanted to sort of give sort of a brief overview of how we think or how we understand these stars to explode. So on the left, I have a keynote drawing of an iron core, where the core is about 2,000 kilometers in radius. And this is sort of what's formed in the late evolutionary lifetime of the massive star, where it has a density of about 10 to the 10 grams per centimeter cubed. And then what happens is this core becomes unstable because pressure support is continuously removed from this core due to weak nuclear reactions in the core. And so the core eventually becomes dynamically unstable, and then core collapse ensues on the order of a few hundred milliseconds, collapsing down to a protoneutron star with these properties of a much smaller radius and a density that's very, very large and near nuclear density. And so during that process, you have something where there's this bounce. Once you reach that stiffening of the core, and you actually form a shock, so a pressure wave at the edge of this iron core that's now become a protoneutron star. And so this pressure wave is what we call, the shock, and it actually is not energetic enough once it's formed to promptly explode the star. So this is something called the prompt mechanism, but it's not energetic enough. And so you need to kind of think about different ways in which you can revive or help increase the energy of this stalled shock to successfully explode the star. And so you have this scenario where you have a bounce, and then you proceed to a stalled shock, where the shock travels outward, loses energy, and then kind of sits in this quasi-steady state where it's considered to be a stalled shock about 100 milliseconds after core bounce. And then on the right here, I have a diagram from an actual simulation with a circle overlaid on top of it, denoting the protoneutron star, where it's emitting neutrinos. These neutrinos are heating up behind the stalled shock, causing convection. So like when water boils, you have this happening above this neutron star. But the edge of this shock surface is actually stalled because it's at this very particular spot where it's balanced with the material falling inwards from collapse and the pressure from the shock trying to recede outward. And so, one of the big questions in some of these, the early work, has been, what revives this stalled shock? What drives successful explosion like we observe? And so what's sort of been the working paradigm is this idea of a delayed neutrino heating mechanism. So you have this protoneutron star, it emits neutrinos, and in some cases, those neutrinos can be absorbed to heat up and provide energy to this stalled shock to drive a successful explosion. And so that's kind of the working idea that we have for these simulations and the things and what we try to do when we simulate these explosions of these massive stars. And so this kind of brings us into the era of 3D core collapse simulations, where you have really cool images. I hope if you don't get anything out of this talk, you at least enjoyed the images. But these are some of my favorite volume renderings of Entropy, which is usually used as a proxy to show different, to show the morphology or the structure of the shock in explosion models. And so I have a bunch of different explosion models that I've shown here from different published works, where the protoneutron star is usually shown at the center, denoted by a specific color, and then you have the shock above that, sometimes stalled, sometimes at the onset or continued explosion phase for these different simulations. The one at the top right is actually from a rotating and magnetic model, where you get a very dipolar feature emerging. And so these are all different pieces that need to go into our simulations. You need to include magnetism, you need to include general relativity, and you need sophisticated and complex non-radial components of the neutrino transport to have a simulation that is of high fidelity and can get you closer to the answer. So that leads us to the problem, I guess, that you have with these simulations and some potential solutions, right? So the next question might be, how do we try to model these stellar explosions? What is sort of the protocol with current generation explosion mechanisms? So typically what's done is you'll take a 1D stellar evolution model using your favorite hydrodynamics code, which are very computationally easy to compute. In a lot of ways, because they can run in a few days. You run that all the way to core collapse, so the start of this explosion phase, and then you map this into your 2D and 3-dimensional hydrodynamics code and explode it. You follow it using sophisticated neutrino transport and so on. And on the right here, what I'm showing is a simulation that does just that. So this is for a 20 solar mass star where we're showing entropy again. So we're trying to follow where the shock is going. So you have the protoneutron star at the center, you have this convection occurring at the top or above the protoneutron star, and the edge of the shock is denoted by this sort of cyan contour on the outside. So for this particular simulation, you actually have a failed explosion. And so the shock initially moves outwards, it looks promising, and then it starts to recede inwards. You have some late time sloshing that occurs about the protoneutron star. This is something that's called the SASE, standing accretion shock instability. But at the end of the simulation, the simulation doesn't explode. It doesn't get energetic enough to actually unbind the stellar envelope. And so the question might be is, what are we missing for this simulation that has, high resolution hydrodynamics? It includes, approximate general relativistic gravity. What are some of the things that we're missing, and why is this model that we expect to explode not exploding? And so there are a couple of things that people have pointed out in the literature being really important to take into consideration that can potentially alter the qualitative outcome of an explosion. And so one of those things is general relativistic gravity. And so I mentioned that earlier, but how you treat gravity in these models is really important. And so if you approximate it, so you use Newtonian gravitational potential, or use an approximated potential that has GR effective corrections to it, those can all alter the properties of this neutron star in the middle, and it can actually change some of the properties that you see for your explosion. I mentioned neutrino transport, so how you capture the heating process, the main heating process in these models is a huge way as well, and that's something that different groups have done studies on, of comparing the different processes done by different groups to see which can have the biggest impact on results. So one of the things I'll be focusing on is the initial model. So if you recall from the previous slide, I had this model that started off pretty spherically symmetric, right? And so that's because you take this 1D model from your stellar evolution, so only the radial component where everything else is spherically symmetric, and you start that as your starting point. But we expect stars, especially near the end of their life, to be very chaotic and nonlinear deep within the interior, where you expect convection to be very non-radial. And so you might be missing a key component that can actually help push a star more towards becoming a successful explosion by missing these non-radial components of the velocity in your simulations. So some of the first work that sort of looked at 3D models of massive stars in the context of near core collapse and in the context of core collapse explosions was a work in 2015 by Sean Couch, Dave Arnett, Frick Timmies, and a couple other co-authors, where they looked at sort of the last 3 minutes in 3D to evolve this star and see how much it differed from what we use in our 1D simulation. So here I'm showing slices in the XY plane where the color map is decoded to the velocity. So a red is higher velocity up to about 500 kilometers per second. Blue is very low to no convective activity. So what we see is the iron core, so in the bottom left of these simulations that we saw in my very accurate diagram of the iron core earlier. And then we have the silicon shell sitting above that. So this is convectively active. So burning shell above that's a turning matter, or it's making the iron core more massive as it gets towards the end of its evolutionary phase, where the convective velocity is sort of increasing in this shell towards the end of the simulation. So we're moving from left to right to later times. And so they used octants, so they didn't include the full 4 pi 3D. They only did for 3 minutes, and they used a very approximated small nuclear reaction network, all of which are approximations that can alter the qualitative outcome, but was a step towards the right direction in terms of using 3D initial models instead of 1D. And so they took this model, followed it to collapse, bounce, like we mentioned, and then sort of exploded it, right? Because they wanted to do this comparison of, okay, this model looks more favorable for explosion. How can we compare that to the 1D models as best way as possible? And so here I'm showing a diagram where on the bottom we have T minus T bounce. So it's essentially the beginning of the explosion phase. And on the y-axis is the angle average shock radius in kilometers. And so looking at the cyan line, which on this diagram is the one that's higher up at late times, you see that the model is reaching higher shock radii at earlier times. And so this is evidence that this model is more kinetically energetic in the different shock radius, and it's more energetic when comparing it to the angle average initial model. So again, promising results for something that we expect to explode. I'll note that the yellow line, so the 1D model still explodes, but even if you follow it out to late times, it might not reach the explosion energies that we would expect for this particular initial set of conditions, 15 solar mass star, as observations might tell us in terms of explosion energy. So kind of driving that same point home, there's another work by Bernard Muller's group in 2017 where they did this sort of same thing, but instead of just the octant simulation, they had a full 4 pi 3D model. So they included the entire star out to, I think, about 10 to the 10, or 1 times 10 to the 10 centimeters. And so a good portion of the star, not the entire star, that's much more challenging to do. And then they exploded those two models and compared them. On the left is a 3D initial model. Here we're showing a ZY slice in the ZY plane of entropy again. So we're trying to follow where this shock radius is going. And we see that on the left, the 3D model is very asymmetric. And if you look at the scale, it's actually at larger shock radii than the corresponding 1D model 1D initial model is on the right. And so this model actually fails to explode, I believe, if I remember the results correctly, and is actually undergoing the same sloshing behavior that we saw in our failed explosion earlier from Sean Couch's group. And so again, making that point that these 3D initial models can make a qualitative difference. Okay, so hopefully I've motivated why I study so far, and now I kind of want to segue into some of the work that we've done recently on 3D simulations of a 15 solar mass star. And so I mentioned earlier that you can map these 1D models from your favorite stellar evolution code. One that I use is MESA. It's partly developed at KITP actually, and so that's something that you can do. You can map this in at the onset of core collapse and then explode that. But what we wanted to do, and sort of building on Sean Couch's work from 2015 and the work of others, is to map a 1D model at a time before core collapse, in this particular case 7 minutes in physical and simulation time, and evolve that in 2D and 3D and capture that hydrodynamic behavior and see if we can compare back to the 1D models, and also if we can sort of build on previous work and see what those bulk properties of this convection looks like, and if it's still yet favorable for explosion. And so on the right, I have a very boring plot, but it's informative if you're familiar with these particular plots. But on the x-axis, we have the specific mass coordinate. On the top panel, we have entropy. Middle is electron fraction. The bottom is the log of the density. So the only important thing about this model is, if you're familiar with these, this is a very boring 15 solar mass model. And so we wanted a model that is pretty representative of what we expect for a 1D simulation of a massive star as our starting point, to then map into Flash, which is our hydrodynamic toolkit that we use to run these simulations, to use as a starting point. So some of the first results that we saw from this, so here I'm showing results for our 3D simulation. We evolved two 4-pi 3D simulations, so including the full star, one with initial perturbations, one without, which is a detail of the work. But what I'm showing here on the right is a volume rendering of this velocity field for the 3D progenitor. And so at the center, we have the iron core, which here I've highlighted with cyan as a iso surface for the iron. It's sort of followed through towards the end of our simulation. We're only showing about the last 100 seconds or so for this particular model. But above that, you can see convection. The purple flow is moving at a speed at about 300 kilometers per second. And above that is a slower moving flow of about 100 kilometers per second, which is showing about the edge or the extent of the oxygen shell region. And so two of the main things that we pulled away from this is that convection can occur at many scales. So you have convection operating at very small scales and very large flow structures that we also were able to identify, both of which have different unique implications for core collapse explosions should this model then be exploded. And then, of course, sort of these different convective features all imply an indirect increase in the effective heating of the neutrino emission behind the stalled shock due to this non-radial convective properties. And so, again, favorable conditions for this model and its explodability. And so looking at this model sort of in a different perspective, here I have an XY slice of this model at a time right before the start of core collapse in earnest, where I'm showing the radial velocity here for this color map, where there's little to no convective activity in the center. So this sort of circular dark region is the iron core, and so it's on par with what we expect. Above that, you have the silicon shell region, where convection is occurring at smaller scales due to the restricted nature of it being between the iron core and the oxygen shell region, which is above it. And then outside of that is the extended oxygen shell region, where we see asymmetric radial velocity properties, and something that has a huge implication for the emission properties of this model and just other properties in general. And so this is sort of in line with what we expect for, or what other groups have been seeing in sort of this sort of asymmetric convection occurring at late times, and something that should be considered as sort of in your starting point for core collapse explosions. And so one of the main takeaways, I wanted to provide takeaways with each of these slides that I show on my work, is that 3D models of massive stars show favorable conditions for explosion, right? And so when you take into consideration these non-radial behaviors, you can identify non-radial kinetic energy and other features that are all sort of leading to this conclusion that they can have a qualitative and direct impact on whether a star explodes and what that explosion properties might look like. So that kind of leads into the next sort of area that I want to talk about, work that's ongoing, where we're looking at the landscape of these progenitors. And so the landscapes of these different initial conditions, different initial masses, and so on. We wanted to see if these bulk properties that we saw from our 15 solar mass model are similar at different initial conditions. And so we're sort of extending on the amount of time that we simulated. So we're using a very similar framework as we did in the previous simulations, but we're extended out to 10 minutes. So 600 seconds, a long time for these simulations. So we're capturing more convective turnover times in these burning shells, again, using the same approximate network. We're considering a different initial masses. So on the right here, I have on the x-axis, the zero age main sequence mass or initial mass for these simulations, these 1D models. And then on the y-axis, we have the compactness parameter, which is a term that's used typically to measure the strength of the depth of the gravitational potential. So higher compactness means you have more mass and interior at a particular radius. And so this is something important about that people have been using in terms of the explodability of models. So higher compactness, you might expect the model to implode, to not be able to escape or become energetic enough to unbind the stellar envelope. So we wanted to sample a range of these initial models in this work. And so each dot is initial compactness and mass for simulation that's ongoing and that we're looking at. And then in the green dot, or the green square, is the compactness for the 15 solar mass model I showed a few slides ago. Okay, so some early results. So this is stuff that's still in work, still in progress. But again, on the right, I'm showing for qualitative purposes the 14 solar mass model for about the last 300 seconds or so. So again, we're looking at this iron core in the center, which is sort of this sphere. And then above that is the oxygen shell convective region. So this one, a few things to point out about this one is that this particular oxygen shell region is much more smaller than the 15 solar mass model. So it's already something that's qualitatively different than the 15 solar mass model. And we see Mach numbers, so a ratio of the velocity to the sound speed in this region to be smaller than the 15 solar mass model. So already a range between these two particular models that are only otherwise one initial mass difference in their initial conditions. And again, convection is occurring at very broad range of scales. So this next plot that I'm showing is for our 20 solar mass model. So it's a different model in this set. We're showing the XY slice, this time of the magnitude of the velocity field. And so if you notice, there's this sort of circular structure in the middle again, where we have the iron core, so little to no convective activity. Above that is this time very thin silicon shell region, where it's pretty hard to make out in this particular image. But above that is, again, this very extended oxygen shell region, which is much more extended than our 15 solar mass model, where velocities are much higher in this, and we see very clear non-linear and perhaps even dipolar flow patterns, which would all have very huge qualitative impacts on the explodability of this model, and Mach numbers that are about 10 times more massive than the 14 solar mass model. And so this is something that we're working on analyzing right now. There's a lot of implications this model might have, as well as the other models, something we're actively working on. So I guess my second sort of takeaway point for these models is that 3D models show a range of convective properties, right? So this argument that you need a set of different progenitors, even if only a difference between initial masses of one solar mass, to kind of get an idea of what these look like in 3D. So you can then at least inform 1D models and sort of start to measure the different properties of them to use them in the cases where 3D models are not available. So one of the last things I'll talk about is, of course, exploding these models. So core collapse supernovae using 3D initial models. I've mentioned explodability a lot, but I haven't shown so far any explosions of my work. So one of the next projects we're looking at, and so something that's sort of ongoing as well, is exploding our sets of models that we have from from the 15 solar mass model paper. And so this is something we're working on right now. We're running a full 4-pi 3D simulation, explosion simulation on Theta at Argonne National Lab, where on the right I'm showing post-bounce time on the bottom, so in milliseconds, time after the start of the explosion. And the y-axis, I'm showing the shock radius. So each different color isn't super important for this talk, other than the 3D model is shown by the gold line at the bottom, which I'm hoping is about to explode. It looks like it's already starting to turn around and sort of lead into the onset of explosion, where this line starts to go up like the other models that have already exploded promptly. But this is something we're working on right now. We're using state-of-the-art, hydrodynamics and other neutrino transport properties. So this is something we're excited to analyze. And so I'd be remiss if I didn't show the actual explosion slice. So this is an XY slice for the simulation for this 15 solar mass model that we're exploding. This particular quantity, again, we're showing the specific entropy, where it's somewhat of a following of the shock morphology, where at the very end you can notice that if you do it sort of by eye, you take the average, you'll see if the shock is sort of getting further and further out. So this is the model. This is a model that's ongoing. That's something that we're working on running right now, and that we're excited to analyze. And so one of the last things I'll talk about for this particular model, this set of models, is that we were able to compute the gravitational wave strain, or an approximation to it at least. Where on the right, I'm showing the post-bounce time again, so after the start of the explosion, and two panels that show the gravitational wave strain, only the plus pole polarization, if that means anything to you, multiplied by distance, which we took to be about 10 kiloparsec, so pretty close. So it would have to be relatively nearby, which is pretty rare, but it's something that if it were, LIGO could potentially detect it. But one of the things that we find interesting about this is that, on the top here, we're showing our 3D gravitational wave emission line for our simulation. And so it's relatively small strain compared to the 2D model, which is to be expected. But two main things is that we see prompt convection, which means that you have this blip of gravitational wave emission at the start of the simulation. This is sort of the beat that you notice about 20 milliseconds. And then the bottom panel, you have something where the strain sort of is weak, and then it sort of amplifies at later times in the 2D model. And so one of the good things about this is that between the blue and the orange line for this one, the orange line uses a 2D initial progenitor, and then the blue line uses a 1D profile as a starting point in 2D geometry. And so already we're able to sort of distinguish between these two gravitational wave emission spectra. And so we could potentially use this to, these new sort of state-of-the-art models where we start from a multi-D progenitor to provide LIGO or other groups with realistic templates for potentially detecting gravitational wave emission from core collapse supernovae. And so one of the last takeaways that I have is that 3D progenitors sort of impact multi-messenger signals in a lot of ways that I haven't shown here. And then at the bottom, I have some volume renderings of this explosion. But yeah, so I'll come to my conclusions now and kind of just gloss over some of these main points again that are showing up out of order. But so we talked about how 3D models are necessary to study stellar convection, and they can actually impact sort of the state of the model near collapse. And so quantifying that is something that we did with that 15 solar mass model, sort of leading into looking at more different initial masses and other properties. We talked about how there can be a range of convective properties at different initial masses, and how all of those have different implications for explodability and our understanding of the last minutes before collapse of these different models. And lastly, we talked about how multi-D models can provide successful, or maybe just closer to the right answer, input for core collapse supernovae, and that are a key component that should be considered in the future, or at least using sort of initial 1D conditions that are informed by these 3D models that are perhaps not otherwise available. So with that, I'll end. I'll tell you that our data are online, most of it at least, and I'll open up for questions. Thank you.
Stefan and Farah, are you moderating the questions today?
Hi, so Professor Alexander normally does, but I can do it if you would like. Oh, he might have dropped off. Okay. Just a reminder, if you have any questions, please put them in the question and answer box so that we can see them. Okay, so the first question that we have is, what role does turbulence play in your research?
Yeah, it's a good question. So turbulence can be really important in a lot of ways. And so that sort of translates to having higher resolution simulations to where we can accurately capture that turbulence. But otherwise, sort of where we're at right now is sort of characterizing the convection right now, sort of commenting on the extent to which these flows are turbulent. And so I think that's something that's really important. And I think that that's why sort of providing these different initial models of different initial masses can help us sort of gauge how important that role is, because right now I don't know if we have a very clear answer. And I don't know if we'd be able to get that clear answer without, sort of honing in on very high resolution simulations for this particular phase of these models.
Okay, the next question we have is, what is being done in the scientific community to make sure that your models match with what is observed in telescopes?
That's a really good question. So there's a lot of things being done. So one particular paper comes to mind, a work by Mackenzie Warren, where he actually looked at sort of 1D, a bunch of 1D explosion models, sort of using the same physics that I used in my explosion simulations, but in 1D, so he could look at a much wider range of properties. But there's a lot of things that you can do to match sort of the expected spectrum for neutrino emission. Characterizing the energy is something. So the energy of the explosion energy, you would need to run the explosion to 8 times, but that's something that you could use to then sort of confirm with what observations what observations are estimating for the explosion energies. So that's some of the ways that we're trying to match with what we're seeing with what we're simulating to kind of guide us with our simulations.
The next question is, could you talk more about the sloshing behavior you mentioned early in the talk? Is there an easy way to understand what causes this? And is it seen in successful explosions as well? Also, great talk. Loved all the visuals. Agreed.
Thank you. Yeah, definitely. So I'm not the best expert on SASE, so the standing accretion shock instability, but it's this instability that can actually happen. It's been discussed a lot, characterized by this mode that is excited in the convection that causes this sort of sloshing. I forget the spherical harmonic that it's excited by, but this is seen in successful explosions as well. So you can have something where you sort of have this sloshing at first, and then that actually sloshing helps facilitate an increase in the kinetic energy behind the shock to drive successful explosions. So sometimes it could actually aid in the successful explosion, but I guess more often than not, as my understanding is that sloshing is kind of an indicator that the shock has receded so much that the only thing that can help get it to that point to explode, if it does, is the SASE mechanism. Otherwise, the shock is too receded.
Why do we expect 2D models to produce larger gravitational wave strains than the 3D? And why does the gravitational wave signal grow after the initial beats?
That's a really good question. So in 2D, convection is much stronger. So you have this scenario where along the poles for certain geometries in 2D, you have convection that is stronger along these poles, and that sort of directly increases the strength of this convection. There's also this thing called the inversion of the turbulent energy cascade in 2D, which actually drives things to larger scales, and so it also helps to facilitate more convectively active shells. And so those are things that translate directly to more energy in the shells and more gravitational wave emission. The reason that you see sort of this amplification at late times in 2D is because you have sort of a periodic nature at late times along these poles as well. And so that's the reason why we need to sort of go to 3D, where we don't have this sort of artificial behavior happening along the poles or the axes for the 2D. But 2D is still good in sort of distinguishing between two similar otherwise models and what the sort of qualitative impacts are between the two.
And that was great, thanks. How much of an effect does a GR treatment of hydrodynamics have on your simulations?
That's a good question. So for my particular simulations, it won't have a huge impact. I think that even for, so for this particular simulation, for instance, we only use so for the treatment of gravity, you can include up to certain spherical harmonic orders for a monopole gravity solver. And so, or for a gravity solver, we only include the L equals 0 term. So we assume a spherically symmetric gravitational potential, which is approximation, but for this particular situation, we're not sort of dense enough and at high enough velocities to where these things have a huge impact on our results. They have a much bigger impact in the actual explosion of the simulation, where, for instance, the explosion simulation uses an L up to 16, which means higher, more sophisticated treatment of the gravity in the explosion simulations. But in the pre-supernova phase, so the 3D stellar convection models, L equals 0 is okay.
What are the hardware requirements needed to do the simulations you're working with in your research? Can any of this be done on a regular desktop?
Yeah, so the pre-supernova models, actually the MESA models, can be run in 1D on my laptop. Excuse me. And I've actually done some of those on my simulation, sort of map them into Flash before. But you can also do it on like a small cluster, like a couple cores or something. The 3D stellar convection simulations, so the simulations before core collapse, those take up to a few thousand CPUs, a few thousand cores. In the very large explosion, the 3D simulation of the explosion, which includes the neutrino transport and all that good stuff, that has to be run on leadership class compute facilities. For instance, we're running those on Argonne National Labs. So those use a couple 100,000 cores at once, which is why the simulation is not done running, because it's very expensive. And so we're in the process of getting that done.
Thanks for the nice background summary. I haven't followed the field in a few years, but last time I did, there was an alternative paradigm to neutrino revival of the shock, where core collapse might be accompanied by jets launched from the proton-neutron star. Is investigating this scenario beyond current simulation capability?
That's also a really good question. So delayed neutrino heating mechanism isn't the definitive answer, and it could actually you can actually have a scenario where explosions are aided in other ways, where that shock is revived in other ways. One is such where you have rotation and you can sort of produce jets in this proto-neutron star. Magnetism also helps in those simulations. And if you recall from that slide I had, that was the particular scenario in one of those simulations at the top right, where we had this sort of dipolar flow that was happening with these sort of jets above it. So those can definitely drive explosions. We expect them to be much rarer, though, than a typical neutrino-driven explosion.
And the last question we have here is, can you simulate in detail how the elements form through nucleosynthesis in the supernova explosion?
Also a good question. That's much more challenging to do. So the explosion we're running right now is really hard, or computationally expensive, I think is a better term. But what you can do, and what a lot of people do, is you can use these things called tracer particles, where you include them in your simulation. These particles will follow some sort of random path throughout the course of the simulation and track the temperature, density, and the different isotopic abundances, because they're much less expensive. So you don't need like as much information on them. So you just kind of throw them into your simulation, and they get a sampling of what the full simulation is. And then you run a post-process on that to get the full nucleosynthesis sort of products from that. So it's something you can do. It's not something we're doing with the simulation, but groups do that as well.
Okay. Thank you so much for all your great questions. And thank you again, Carl, for your amazing talk. Thank you, everyone, and we hope to see you next month at our next talk.
Awesome. Thank you so much for having me. All right. Bye.
Thank you.